Okay, so this is going to be the data reduction for head loss in a pipe system. Let's take a look at the data reduction that we have to do. So if we look at 2 through 5, we need to find the minor loss coefficient for a lot of our components, and then we're going to plot that against the Reynolds number for a lot of these. Okay, and here we're going to plot against a dimensionless quantity r divided by d, the radius divided by the diameter. You don't have to do number 6 here, the area analysis. You can skip that. Number 1 here, so we're going to find the friction factor F in the straight pipes A and L. You don't need to fit it with a power function, just like the last labs. So let's go up and we'll take a look at these sections A and L. Okay, so for section A here, this is on the dark blue circuit of the pipe system, and section L, that's on the light blue circuit. If we look at this diameter, it's 13.7 millimeters. And then here for section L, the diameter is 26.4 millimeters. So I'm going to say that dark blue, this is going to be the small diameter, and the light blue, that's going to be the large diameter. Let's go to MATLAB. So if we look right here for D1 and D2, D1 was the dark blue pipe, and we have 13.7 for the diameter. And then for D2, that was the light blue pipe with 26.4 for the diameter. Okay, so you can take pause the video here or take a screenshot so you can type all of this out. I'm starting out the script. As always, I'm going to clear the memory first. Then I'm going to specify the constants that we have. So we have gravity, we have the water viscosity, the water density, the diameters of our pipe sections A and L, and then the length of our pipe sections for A and L as well. So we have 901.7 for the light blue pipe, which we see here. Then we have 914.4 for the dark blue pipe, and that's written out right there. Okay, then we have some conversion factors. So centimeters to meters, millimeters to meters, milliliters to meters cubed, inches to centimeters, and inches to meters. Okay, then we're going to initialize the array sizes. So big Q, that's going to denote a mean volumetric flow rate. And then I have LB for light blue and DB for dark blue. Then we have little q, that's just going to be the volumetric flow rate that we found for each percentage of the maximum flow that we did. So we have 9,5. So let's go here. We'll go to the flow rate. So we had 9 settings here for the flow rate, for the maximum flow rate, and then we had 5 runs. So that's why we have a 9,5 for the flow rate right here. And then for the mean flow rate, we're just going to find that mean flow rate that we have for each of those percentages. Okay, then the volume. So again, we did that for light blue and dark blue. Same kind of thing. Our volume is here. So we had the volume for the 9 percentages of the flow rate, and then we had 5 runs. Okay, so we're going to go down. Same thing for the time. We had the 9 percentages, and we had 5 runs. Then we have the friction factor for the small pipe, and then we have the friction factor for the large pipe. Okay, and then we have our expansion and contraction. So we just had one of each, and we did it for the 9 percentages. And then we have the minor loss coefficient for the bends. So for dark or for light blue, we had 3 bends, and for dark blue, we had 2 bends. And then our valves here, we had one valve for the dark blue and one valve for the light blue. Okay, the next thing I've done is imported the data from Excel. So here we have the head range. So this is going from B2 to H10. So we're starting at B2, and we're going to H10 right here. And that should have been actually for this one. So for this spreadsheet right here. So B2 to H10, and then we're getting our time data. That's going to be B2 to K10, so that's right here. And this is going to be for both the dark blue and the light blue. So you see I'm on dark blue right now. If I go to light blue, it's going to be the same rows and columns that we're importing. Okay, so then I'm going to then import the pressure data for the light blue. So for this one, it's from B2 to L10. And now I'm going to specify A, B, C, and D as variables. So A, that's going to be the H range that we just imported here. So A is going to be all of this right here. And then B is going to be all of this. C is going to be all of this. And then D is going to be all of this. Okay, so now I have all this code here, so we're going to sort the raw data into separate data arrays. So first off, the head data, we're just taking the head data that we have and we're converting it to meters. So I'm taking all of this data and converting it to meters, and also the same for the dark blue data here, converting that to meters. So dark blue and light blue. Next up, we're going to sort the volume and the time data. Okay, so this is going to be code that's similar to what we did last time to kind of sort through this data here. So in this column, this is time, and then in this column, all of this is volume. Okay, so I'm doing for I equals 1 to 5 for the 5 runs that we have. Then I have I1 equals 2 times I minus 1 plus 1, and I2 equals I1 plus 1. Okay, so I'll just do an example for this line of code here. So if we want to get the volume for the light blue circuit, I'm on this light blue flow rate data. So if I want to get this volume, it's going to be this. I want to get this column right here, and this column, and this column, and that column. So let's do for I equals 1 right here. So then that would mean I1 equals 2 times 1 minus 1, so that's 0. So I1 is going to be equal to 1. Okay, that's fine. And then I2 is going to be I1 plus 1. That's 1 plus 1, so I2 equals 2. Okay, so if I want this volume, I'm going to say the volume of the light blue circuit. I want to get all of the rows, and then the ith column. That's going to be for each run. Then I'm going to say that this is equal to, again we want the volume for the light blue circuit, so that's on sheet D here. I want to get all of the rows, then I want the I2 column. Okay, so we just did this for the counter of I equals to 1. So I2 is going to be equal to 2. So it's going to get this column right here. Because remember, we didn't import this first column here. So column C is the column 2 that we imported into MATLAB. Okay, I hope that made sense. If not, kind of, go back and listen to that part again. So either way, it's going to sort through our data, so we get our volume data all here, and then we get our time data in a different array. Okay, so we're doing that for the light blue circuits and the dark blue circuits for the volume and for the time. Okay, the next thing I've done here is converted the measurements to SI units. So we're taking our diameters and we're going to convert them to meters. Then we're going to take our lengths of the pipe sections and we're going to convert those to meters as well. And then here is something that's a little weird. I have these two constant values, so constant 1 and constant 2. The only difference between the two of these is D1 and D2, where remember we're looking at the sections of pipe A and L. So this section here, and then this section here. So let's go back here. I have constant equals 0.125 times gravity times pi times the diameter to the 4th. So we're just doing this so we don't have to type as much later on in the data reduction. So what this value is if I'm trying to find, for example, the theoretical minor loss coefficient for an expansion, that would be equal to the minor loss, or the minor head loss for that expansion, divided by the volume squared, or the velocity squared, divided by 2 times the gravity. So if you were going to plug in for this velocity here, knowing the mass flow rate equals, Q equals AV, then you solved for the velocity. If you plugged all this in, then you would get this new formula right here. And then this constant value that we have is just the denominator here. So we're just, we're saving time by just having a new variable that we can type out in the denominator instead. And then our flow rate, that's going to change, for different runs. So we're going to leave that there so we can type that in as we go on in the data reduction. Okay, so now we're ready to get started on our calculations. So the first one we're going to do is find the mean flow rate. So we want to find the mean flow rate for all of the 9 settings that we had on the rotometer. And for each of those 9 settings of the rotometer, we did 5 runs to find the flow rate. Okay, so we have the flow rate for all of the 9 settings, and then for all the 5 runs, so we have the flow rate for the light blue circuit, and we have the flow rate for the dark blue circuit. And that's just going to be our volume divided by the time it took. Okay, simple enough, so we get that. And now we want to find the mean flow rate right here. Okay, so that's just going to be another simple coding line here to find the mean flow rate. We're just going to find the mean flow rate for all of those rotometer settings. So once we compute that and we run the code, then if we look at the mean flow rate for the light blue circuit, I have one column, so I have all 9 settings that we had for the rotometer. Okay, so what we have here is we're looking for the friction factor in the straight pipe. So for this, we're going to be using this formula. I'll show it here. So we're basically just going to solve for the friction factor here. So we're doing F equals this major loss divided by all of this right here. So we're going to plug that in. And now if you take a look at the code, I have this constant value again. So an easier way to see this is if I go here to this note. So here is the friction factor that we're trying to solve for. That's from this equation right here. And then if we plug in for the velocity, knowing that Q equals A times V, if we plug all of that in, then we're going to get to this formula here. And then in pink, that's the constant that we just coded out. So if we compare this with this formula here, if you compare these side by side, you'll see that they're the same. The only difference is our diameter for each circuit. So we have D1 and then we have D2. And then of course the taps that we used, they're going to be different as well. Okay, so let's take a look at this. Let's take a look at the light blue, just for example. So here we're doing for runs 1 to 9, that's for the 9 rotometer settings. Okay, so we want to compute this friction factor for all of those 9 settings. And now what I'm doing is I'm iterating on that run, so we have I right here. And then this 2, that's going to correspond to the tap that we had for the piezometer. Okay, so this is for the large diameter pipe. So let's go back here. Where is it at? Down, yeah, here. Okay, so that's for our light blue pipe. Okay, so this is for section L here. So we need taps 8 and 9. Okay, so remember that just because that's taps 8 and 9, our columns are going to be different. Okay, we're on the light blue sheet right now, and we imported all of this data into MATLAB. So we need taps 8 and 9 over this length of pipe L. So that's columns 2 and 3 here. So that's why we have a 2 and 3 here. So, you know, it can get confusing. We have a lot of bookkeeping to do with this code, so just try to keep things straight in your head. Okay, so you'll type in this code, and then we're also going to find the Reynolds number for each of these. If we go back to our spreadsheet, that's given right here. Okay, so you'll plug in for that, noting the different diameters. And now what we're doing here is we're removing zeros from the data set. Let me take this out. I'm going to run the code. If I look at the friction factor for the small diameter pipe. Actually, that's not a good example. Okay, let's go. The friction factor for the large diameter pipe. I have 3 zeros here. So what I want to do to plot this better later on is I need to get rid of these zeros. So to do that, I have this code right here. So right now I'm telling MATLAB to look at this large diameter pipe and take out the zeros for rows 1 and 2. Let's go back here. I have zeros in 1 and 2. I want to get rid of those. I also want to get rid of this, but we're going to do that later on. That's with this code right here. So let's take that out. Now I'm going to run this code. Now if I go back to this friction factor for the large diameter pipe, now I took out those first 2 zeros in the first 2 rows. Now I have a 0 in the second row again. So now that's why I had this code right here, where I'm going to take out that 0 in that second row. I can now run that. Now all these zeros are gone. Okay, I'm going to take all of this out again really quick. Okay, so if we look at the Reynolds number here, I didn't have any zeros in here. However, we need to plot the friction factor against the Reynolds number. That's what it says right here. I just took out some zeros in my large diameter friction factor. I took out 3 zeros, so if I go here, I have a, I need to update this. Run it. Okay. I have a 6x1 vector here. My Reynolds number, that was a 9x1 vector. So what I need to do in order to plot these vectors, they need to be the same length. So now I need to update my Reynolds number vector right here to also be 6x1. That's why I have this same kind of logic in this code here for the Reynolds number for the large diameter pipe. I'm going to take out those same row entries that I took out for the friction factor. So now my Reynolds number for the large diameter pipe, that's also a 6x1. because those vectors are the same length now I can plot them. I hope that made sense. It's a lot of stuff that we have to do in this lab, and I know it kind of sucks, but that's the way it is. Okay, so question 2 is for an expansion and a contraction. So take note of this formula, and it's going to be, let's go, it's going to be this formula right here. 2.22, that's for an expansion, and then for a contraction, 2.24. So again, we're using our constant value here, and it's the same kind of logic that I explained up for the friction factor. And you'll see here, I also took out some values for the friction factor. So if I run my code, and I go to, for the contraction, that's now a 6x1, so remember for this, we're going to plot our minor loss coefficients against the Reynolds number. So because of that, our vectors, again, they need to be the same length. So I want to take out each of the rows here that I took out for the corresponding Reynolds number for that, corresponding run for the rotometer setting. So that's why I'm following that same logic that I used up here for the Reynolds number. Like that, okay, so now we're on question 4 for bends. So I typed out quite a lot of code here, so I'll try to explain it all. So first off, let's just look at one line of code here for finding the minor loss coefficient. Okay, so the minor loss coefficient is given by equation 2.27. So we're going to have a difference in height from our piezometers, and then we're also going to have a major loss component as well. Let's go to equation 2.18. So here's our major loss component. And so what I've done is I basically subtracted this part out after we had the difference in height from our piezometers. So again, though, we have our constant here. So following the same kind of logic that we've been using, so we have that in here as well. And then you'll see that I have this, I'm multiplying it by L, so that's this L over D right here. So you can see L is equal to L divided by D. So, where am I getting these numbers though? Let's go to the bends. Okay, so that's going to be right here. So I have 0.94, 0.93, 0.92, 0.935, and 0.88. And I converted those to meters. Then we're dividing it by D1 because again, we need that L divided by D ratio that we have in equation 2.18. Okay, so I'm also calculating the Reynolds number because we need that to find the friction factor, which we're finding using the Blausius equation. That's right here. And then that friction factor is used in that formula that I just discussed. Okay, so we're going to do that for the dark blue and then for the light blue as well. Okay, and then now again what I'm doing here is I'm shortening my vector. So let's take this out. If I run this and I go to KBL and KBD, we see that they have a length of 9. Okay, we have 9 columns. Actually, we have 9 rows, sorry. Said that wrong. Okay, so let's take a look at this dark blue. So we have 9 rows and then we have 2 columns because we have 2 bends for the dark blue. But I need to shorten these out. So let's look at what question 4 requires. It says to plot the average minor loss coefficient KB versus the dimensionless quantity R divided by D, where R is the radius of the bend. Okay, so we have, in total, we have 5 bends. We had 2 from the dark blue and then 3 from the light blue. Okay, 3 in the light blue, 2 in the dark blue. So again, if we want to plot our minor loss coefficient for the bends versus this r divided by d quantity, then our vectors need to be the same length, which is 5. Okay, and then we'll type out r divided by d later on. Okay, so what we have here is I'm again going to shorten my vectors. So we're going to do the same kind of thing that we did before for this section and this section. So for the light blue pipe system, I'm going to start it by taking the first two values like that. Then I'm going to take out the second value after that, just like that. Then for the dark blue, all you have to do for that is just take out the first value. Okay, so we're going to do that. Okay, now we need the mean minor loss coefficient for these bends. So what I'm going to do is I'm going to take the two values. I need two values here for the dark blue, and then I need 3 values for the light blue. Okay, so we're going to iterate this from 1 to 2 for the dark blue, and then iterate from 1 to 3 for the light blue. So now if we run this code, now we have a 5 by 1 for the average minor loss coefficient for the bends. Okay, so now what I've done is I've added this one line of code. So again, we want to plot these minor loss coefficients for the bends compared to the value r divided by d. So we need the radius for all of these bends. They're given right here. Okay, so for the minor bend, that's just going to be 0. It's bend B right here. For the STD elbow, that's going to be 1.5 times the diameter. That's C right here. And then we have the radii listed for the rest of the bends right there. And then again, we're going to convert that to meters. Then we need to divide it by the diameter as specified in the data reduction, or divided by d. So if we run that code, then we have r right here. We have our 5 values that we need. And now we can plot our minor loss coefficient, the average minor loss coefficient for the bends versus this radius divided by diameter dimension. Okay, so now we're on the last question. We need to look at the minor loss coefficient for the globe valve and the gate valve that we had. So for this, the equation is pretty simple here. It's just 2.31. And for that, we're going to be using our constant value again for both of these. And then we'll just plug in. And remember, we're going to shorten our vectors for the light blue and the dark blue, just as we've been doing for each of these questions. Okay, so you can go ahead and run that code, and then now we're going to be ready to finally plot our data. Okay, so question 1, we just have to plot the Reynolds number versus the friction factor. So go ahead and we type in all this code and we run this. You should get a plot that is similar to this. So we have Reynolds number here, and then the friction factor here. And then we have a legend for the dark and light systems as well. Okay, for questions 2 and 3, we have the expansion minor loss coefficient and the contraction minor loss coefficient versus the Reynolds number. We can plot those out. Here's our contraction. Here's our expansion. And this was figure 1, you already saw that. Okay, and then we have questions 4 and 5. So we have bends minor loss versus the dimension r divided by d. And then we have the minor loss for the valves versus the Reynolds number. Okay, so pretty simple code once again. I made one adjustment here. I put legend 1 up here and then legend down here. Basically, if I run this like this, I'm going to get this error. So what I have to do is change this to legend 1. And if I run it, then everything is okay. Now I have a legend on this graph as well. Okay, so your graphs should look something probably similar to this. Of course, there might be a little different, but this is the general trend. Alright, so that's it for this video. I know it took a while, and there was a lot of bookkeeping that we had to do, so it's a little complex, but hopefully you've understood it and you can go ahead and do your own data reduction. Alright, so I'll see you next time.